Alright, so we're going to go ahead and fast forward this chapter as much as we can by clipping out a bunch of stuff that you typically would have learned, and I'm just going to try and make it as super simple and easy for you as possible. So the next two lectures are going to be about gas laws, and several of the gas laws focus on simply four variables: pressure, volume, temperature, and the number of moles. Okay, so here's what you need to know before we move forward into calculations. Pressure, for right now, it doesn't matter what unit you use. We can use atmosphere, we can use torr, we can use kilopascals. The most common ones we're going to use are kilopascals and atmosphere, but you can use any one. And the same goes for volume. Typically the most common unit is going to be liters, but you can use any unit. You can use milliliters, you can use cubic centimeters, it doesn't matter. And N is very straightforward. N is just moles. However, there is one very, very important thing that we have to consider, and that is temperature. Temperature cannot be any unit. It cannot be Fahrenheit. It cannot be Celsius. It must be Kelvin. That has to be the unit when we do calculations involving temperature. So as we do calculations involving these variables, what we need to know, or what we need to sort of keep in mind, is it turns out there's a relationship between certain variables when some variables are held constant. What that means is they don't change. So just a quick, for example, let's say you have that little helium tank. So inside you have a bunch of helium atoms. If you were to heat up this tank, generally what would happen is the temperature inside of this tank would increase. So we know that temperature would change. And if the temperature of these particles is changing by increasing, its kinetic energy is going up, and therefore its pressure will go up as the collisions along the inside of the wall increase. However, the number of particles does not change, and since your helium tank is basically this steel container, it really has negligible change in volume, so we say the volume doesn't change either. So here we have a relationship between temperature and pressure. So let's go ahead and jump into a couple of laws. Alright, the first law we're going to talk about is called Boyle's law. Now, had we had more time, I would have mentioned some things about Boyle and how he worked with gases, but we're going to skip all that. So the main thing that we have to keep in mind is basically he gave us a relationship between two variables. He gave us a relationship between pressure and volume. And the equation that we're going to use is written like this: P1V1 equals P2V2. The way we use this equation, I wrote the wrong number. P1V1 equals P2V2. So the way that we use this equation is P1V1 represent the pressure and volume before a change occurs, and P2V2 represent the pressure and volume of a system after a change has occurred. And when we say change, what we mean is one of these is going to change. So for example, your initial volume will change to a different volume, and that is going to make your pressure different as well. Now, the only way that Boyle's law works and is reliable is temperature and the number of moles, or the amount of particles, is constant. If they're constant, if we were to put them in the equation somehow, let's just say it was like T times P times V, and it was the same thing on the other side. Well, if it was the same on both sides, mathematically they could just reduce themselves and they wouldn't come out in the equation. So the general idea is, if it's held constant, it does not come out in the equation. So how does this equation work? When your temperature and number of moles are held constant, pressure and volume are inversely proportional. What that means is if you have an initial pressure and initial volume, and let's say you increase the volume. So let's say we have pressure and volume. Let's say you have an initial pressure and initial volume. If you were to increase the volume, the pressure would decrease, and it would do it proportionally. So what that means is if you double the volume, then the pressure decreases by a factor of 2. If you triple the volume, then the pressure decreases by a factor of 3. That's the way it works. If volume were to go down, pressure would go up. So you can just think of it as in terms of inversely proportional, they're opposites, right? So if one goes up, the other goes down. And here we have a graph that kind of shows that. This is just a generic gas sample, but as you increase the volume, if you have the same number of particles, you have more space that they're going to take up and less collisions along the walls, because now there are more wall space to collide with, but the same number of particles, so the pressure is going to drop. And so let's solve a quick Boyle's law problem. So let's say we have this problem right here. So we have to figure out how to solve a problem. We've got to figure out what gas law to use after reading the question. So right now, we don't necessarily know which gas law to use, but if we look at it, it says a 2.50 liter sample of anesthetic gas at 1.1 atmosphere increases to 6.48 liters. What will the new pressure be if the temperature remains constant? So what I recommend is underlining or highlighting or circling the given information to us. So we know that we have a 2.5 liter sample. We know that its pressure is 1.1 atmosphere. And then we know that it changes to 6.48 liters, and it wants to find the new pressure. And then the big ol' hint is temperature remains constant. Now we have no reason to believe that the number of gas particles has changed. Therefore, knowing that we're looking at a situation that compares volume and pressure with constant temperature and the number of moles, we must be using Boyle's law. P1V1 equals P2V2. So it's as simple as this. Plug in for your variables. P1, V1 are your initial pressure and initial volume. So we know that the initial pressure is 1.1 atmosphere, and we know that the initial volume is 2.50 liters. We know that the volume has changed to a new volume, V2, 6.48, and it wants to know the new pressure, which is P2. So why don't we just go ahead and rearrange this equation to something a little bit friendlier. We know that we want to solve for P2. So let's isolate it. Let's throw everything else to the other side. If we have V2 on that side, divide both sides by V2, and we'll have our equation. P1 V1 over V2 equals P2. And we know all those numbers, so we can just plug them in and calculate. So we got 2.50 times 1.1 divided by 6.48. So our units, liters, will be reduced. We'll be left with atmosphere, which is what we want, and it makes sense because we're looking for pressure. So our final pressure, or P2, is going to be 0.42 atmosphere. Now we need to see if this makes sense. Our equation is P1V1 equals P2V2. So we went from 2.50 liters to 6.48 liters. That means that our volume went up. And remember, we said they're inversely proportional. So if our volume went up, that means our pressure must go down. And we started off with 1.1, and now we're at 0.42. So it did go down, so we're on the right track here. And that's how you use Boyle's law to solve a problem like this. Alright, so yeah, I'm playing around with different drawing techniques. So the second law that we're going to look at is called Charles's Law. And really the only thing I'm going to tell you about him is that he's French and he is a physicist and balloonist. Alright, so the equation that we're going to be using here is represented like this. V1 over T1 equals V2 over T2. You can use this gas law to solve problems when pressure is constant and the number of moles is constant as well. So the only things that are changing are volume and temperature, then we can use Charles's law to solve it. And in this relationship, you notice we have V over T. The kind of relationship that it has, or the kind of relationship that volume and temperature has, is directly proportional. So what that means is if the temperature increases, volume increases. If the volume decreases, temperature decreases. They move in the same direction at the same magnitude. If the volume were to be doubled, then the temperature would be doubled. If the volume were to cut in half, right, be reduced by a factor of 2, then your temperature would cut in half as well. So they move in the same direction at the same ratio. So let's go ahead and solve a problem using Charles's law. Alright, so here you have a question. A balloon inflated in a room at 25 degrees Celsius has a volume of 6 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What is the new volume if the pressure remains constant? So again, what if you just didn't have, what if you weren't told that this is a Charles's law problem? How are you going to figure that out? Well, go through the problem and find the important information. So we have a balloon and we're given the initial temperature of the balloon. And we're given the initial volume of the balloon. The balloon is heated, so we know that there's a temperature change. Its new temperature is 58 degrees Celsius. What is the new volume is what we're looking for if the pressure remains constant. So we have no reason to believe that the number of moles has changed, and we're told that pressure is constant. So pressure and the number of moles is constant, and the only things that are changing are temperature and pressure. Therefore, we can use Charles's law. V1 over T1 equals V2 over T2. I'm sorry, I just realized that I said the only thing that was changing was temperature and pressure, and that's incorrect. The only thing that's changing is volume and temperature. So we can go ahead and use this law. Alright, so let's figure out what it is we're looking for and any other calculations that we need to make. So we are going to use this law because pressure is constant and the number of moles is constant. So V1, T1, V2, T2. So we're going to use those for variables, and let's see which one we're going to solve for. So V1 is the initial volume. Well, if we go through this again, we know our initial values. We know that the initial volume is 6 liters. We know that the initial temperature is 25 degrees Celsius. We know that the final temperature is 58 degrees Celsius, and the final volume is something that we are trying to look for. So the one that we don't know is V2. That's what we're trying to solve for. But we do know the other values. We know that the initial volume is 6.00 liters, and we know that the initial temperature is 25 degrees Celsius. But, as I mentioned earlier in this lecture, when we're working with temperature, it must be in Kelvin. Therefore, we have to convert it. Every time when we're using these gas laws, we must make sure the temperature is in Kelvin. So 25 plus 273 comes out to 298 Kelvin. And the final temperature was 58 degrees Celsius. Obviously, we need to add 273 to that, and we get 331 Kelvin. So if we look at our equation, V1 over T1 equals V2 over T2, and we're solving for V2, well, why don't we just isolate V2, rearrange the equation? If V2 is being divided by T2, we can multiply both sides by T2, and our equation will be V2 is equal to V1 times T2 over T1. So this is what the equation will look like when we're trying to solve for a new volume. And since we already got the numbers, why don't we just go ahead and plug them in and solve for it. V2 is equal to V1 is 6.00 liters times T2 is 331 Kelvin, all divided by T1, which is 298 Kelvin. And let's see what we get. I got 6.66 liters. Now let's see if we did this right. Does it make sense that that's what we got for our answers? Remember that the relationship is directly proportional between volume and temperature. What that means is if one of them goes up, the other one goes up. If one of them goes down, the other one goes down. The ratio at which it goes up is the ratio at which the other one goes up. So volume is doubled, temperature doubles. If volume is cut in half or multiplied by 1/2, then the temperature will also cut in half. That's how it works. So if we look at what happened, temperature went from 25 degrees Celsius to 58 degrees Celsius. So temperature went up. So if it's directly proportional, we expect an increase in the volume. Well, it went from 6 liters to 6.66 liters. So we definitely had an increase. So this problem seems to make sense, and our answer seems plausible. So this is an example of how you would solve a gas law problem when pressure and the number of moles are constant, and V and T are the ones changing. All right, now we're going to go ahead and move on to the next gas law. And as I said, I've been playing with different drawing techniques, so you'll see on the next slide what we have. Okay, this next one's going to be called Gay-Lussac's law. And I'm not going to lie, I just kind of freehanded this drawing. I actually pulled it from this photo here, so I know you probably can't tell. This is the one from the internet, and this is the one that I drew. I think it's just a couple of minor details missed, but other than that, identical. Okay, so hopefully you're getting the idea. We're looking at variables. Some variables are constant, some variables are changing. We get an equation. So I'm just going to tell you. The equation for Gay-Lussac's law is P1 over T1 equals P2 over T2. So what that means is your constant variables are volume and the number of moles. When those are constant in a gas problem, we can use this equation to solve for a new pressure or a new temperature. And again, just a side note, since we're using temperature, we do need to make sure that our temperature is in Kelvin. For pressure, it does not matter what unit we use. So anytime you see fractions like this, it means there's a direct proportionality between the variables. So what this means is if one of these goes up, like temperature, pressure goes up. If one of these goes down, the other one goes down. And by the same factor, if we double the temperature, we double the pressure. If we cut the temperature in half, we're going to cut the pressure in half. That's how it works. So now let's look at solving a problem using Gay-Lussac's law. Alright, so I kind of got tired of writing the problems, so I went and just took a picture of one. So here it says the pressure in an automobile tire is 189 kilopascals at 10 degrees Celsius. If at the end of a trip on a hot sunny day, the pressure has risen to 405 kilopascals. What is the temperature of the air in the tire? And we're told that the volume has not changed. So, if volume is constant and the number of moles is constant, we know that pressure and temperature are changing. We can use Gay-Lussac's law. P1 over T1 equals P2 over T2. So let's see what we know and what we don't know. P1, T1, P2, T2. So we know that our initial pressure is 189 kilopascals, and it's perfectly fine. We don't have to change to any kind of unit. Temperature is 10.0 degrees Celsius, but it needs to be in Kelvin, so we're going to add 273 point, we'll round, 0.2. So that's going to come out to 283.2 Kelvin. And actually, let me just go ahead and clean it up there. Alright, so 283.2 Kelvin. The new pressure is 405 kilopascals. So if the pressure is going up, we expect the temperature to go up as well. And we're solving for T2. So if we're solving for T2, we need to rearrange the equation. And I know some of you might not like it because T2 is on the denominator, but this is something you can do to sort of fast track these kinds of equations. Anytime your variable is on the denominator, you can just flip the entire equation or relationship, basically reciprocate everything. So if P1 over T1 is equal to P2 over T2, then that also means that T1 over P1 is equal to T2 over P2. And since we're trying to solve for P2, we can just, for T2, we can just send P2 over to the other side. So that actually turns into T1 times P2 over P1. And we have those numbers, so we can just go ahead and plug them in. And then we can just go ahead and compute this. And so our new temperature in Kelvin, as we said, is we expect it to increase. It comes out to 607 Kelvin. And this is how you use a Gay-Lussac's law to solve a problem when your temperature and pressure change, but your volume and number of moles remains constant. So we'll just look at those three laws for today, and I'll send out an assignment shortly.